Hi everyone, welcome to my channel. This video is part of a playlist on AKS, Azure Kubernetes Service Networking. What you see on my screen is a layered architecture diagram created using Draw.io. And I have created detailed videos. If you're interested in creating these type of diagrams, be sure to check out my GitHub repo link below. Now, today we're going to talk about Azure Container Network Interface, Azure CNI, which is a networking model that manages how pods communicate within the cluster and with external resources. So today specifically we'll talk about Azure CNI. In the last session we covered Azure Kubnet networking. So what we will do today is we'll start with a recap of Kubnet. We'll understand the differences between Kubnet and Azure CNI, understand the key design points, and then we'll jump on to VS Code and build the cluster from scratch. And while the cluster is building, and we'll jump back into Draw.io, look at the core concepts, different inbound and outbound flows. Then we will run some validations from the command line and portal, and then we'll close it out with some quick troubleshooting tricks. So let's have some fun. If you're following along with me, this is a typical starting point that I use where I have a classic hub and spoke architecture. So let me remove the cluster first so I can show you the hub and spoke architecture. So this is what I call a brownfield environment. We have a existing hub, we have an existing spoke, we have a branch, and we have a site-to-site VPN between Azure and the branch. Okay, and of course the VNet peering between the hub and the spoke. So with that, we will we will build out an AKS cluster. So let's build out an AKS cluster, and this AKS cluster will attach to the subnet, to an Azure subnet. So these nodes will attach to the Azure subnet that already exists. So this is what an Azure CNI architecture would look like. You would have two networks, node and the pod network. Notice they're both on the Azure AKS subnet. And this cluster network is on its own within the cluster. Now, if we differentiate that with the Kubnet, just to recap what we did there, as you notice, Kubnet had three separate networks. The pod network was different from the node network. And you will see that in case of Azure CNI, both the node and pod are the same network, 172.16.240. Okay, so that's the key differentiator. Now, if you think about the use case for this type of network model, is that in the previous one, you had a lot more IPs for pods. Here you're sharing pods are sharing the network with the node. So you have to plan your IP addresses ahead of time, and you are limited by this AKS subnet. So if you have a /24, both your nodes and pod will share that. The good thing about that is that it gives you these pods are directly on the Azure subnet. So you have direct communication to Azure resources like VMs and databases from within the cluster. You don't need the NAT as it was required in the CNI, in the Kubnet network. So that those are the key differentiators. So with that, let's go back into our VS Code screen here, and we'll get started here. So the first command I'm going to do is log into Azure. If you haven't done that, you can do that, and this command will validate. In my case, I'm already logged in. there is this useful command called kconfig get context, where if you have multiple AKS clusters, you can see that multiple clusters get shown over here. So let's delete let's delete this one because we're going to create a new one. This must be an old one that I created. So we will delete this one. So we'll just say delete, and we will now, if we do up arrow the command, we no longer see this one. This is the old one that we used for creating the Kubnet cluster. So let's go through the defining the variables. First, I just remember that I have aliased k to be kubectl, and that's why I was able to use kconfig. Let me put this above here so that it's in the right order. Oops. So now that we have deleted the old context, let's define these variables. You can define your own. These are my variables. I'm going to go ahead and paste that. So if you look at it, the important thing to remember here is that this VNet and subnet already exist. This is the VNet resource group as opposed to a new resource group that we would create to create the AKS cluster. So this is the AKS cluster resource group, and this is the resource group where the VNet already exists. And then you see the plugin that we are using is Azure. Before we were using Kubnet, which is the default plugin. So let's create the resource group. So we'll create the resource group. We'll create the container registry. And you can see a lot of the comments here explain what each of the commands is doing. And then we will grab the VNet ID of the existing VNet. We'll grab the subnet ID of the existing subnet based on the name variable that we have given. So let's do that. We'll do this. So now that we have, as you can see, it's the Azure AKS subnet and VNet. Let me show this to you in the portal as well, the existing subnet. So you could see that I do have an existing subnet 172.16.240. Our KubeNet was in 239. So that's my existing subnet within the VNet. So going back here, let's create an identity. And this is the identity that is assigned to the AKS cluster. And you can list the identity in using this command just to validate. And then we'll carve out this principal ID and this ID and save it into two different variables. So let's do that. And I always have an echo command after just to make sure that the variable has the right information. And then what we will do is, this step is very important. Basically, it grants this principal permissions to manage the resources within the VNet. And if you don't do this, some of our deployments will fail later. So this is another troubleshooting trick that I mentioned in my previous session as well. So now that we have all of our variables defined, we are ready to kick off. I need to fix this. I think this should be $sign. So we can use this now that we have this defined as a variable here. So this should be identity ID. All right, so we have this defined as a variable, so I just fixed that. So let's take a quick look at what this AKS create command does and it uses. It's going to create a 3-node AKS cluster. It's going to get the name AKS cluster. And if you notice, there is a cluster name and then there is a DNS name. So if we go back to, in my case, the cluster name and DNS name are the same, but this DNS name has to be unique across the region. It's a unique FQDN across that region. And this cluster name has to be unique within the resource group. And in my case, I made it the same. And the service title is nothing but the cluster IP or the cluster network that you saw in the diagram. This DNS service IP is used for DNS resolution, and it is used by core DNS to provide DNS resolution within the cluster. So that's what this IP is. And then we have the subnet ID, and then we're going to have maximum of 30 pods. And this is the verbose. It's good to have this command kicked off using the verbose mode so we know what's going on. So let's go ahead and kick off this thing. Assign identities. Okay, so something is not right. So let's look at how we did it in our Kubnet. I believe in the Kubnet we called it identity underscore ID. So let's see what the problem is here. So identity underscore ID. So that's the variable. Okay, so it's the variable is actually, if we look over here, it's yes. So the variable here is called identity underscore ID and not NN identity. Okay, so let's fix that. And let's close this KubeNet one. So, all right, so now let's kick it off. Okay, so it's like it's happy and it's going. So while the cluster is deploying, let's take a look at the draw and see what we're going to do next. So far we just kicked off the deployment of this cluster. So we expect that when the cluster is finished deploying, these nodes will get an IP from this network, the 172.16.240, and we will validate that. And then we will do a deployment of this these pods, which is called a deployment, and it's also sometimes referred to as endpoints. And these pods will be listening. That deployment will create 3 replicas, one on each node, and it will be running an Nginx image and expose the port 80. We will also look at the YAML, but in the draw we're going to look at how, at a high level, how this is designed to work. So now we have endpoints, and remember when we do the deployment, it does the pods, and when we do the service, it exposes these pods using what's called a service, which behind the scenes spins up a load balancer, external load balancer, and we can also define an internal load balancer. They're both of the type service in the YAML file, but we could define whether we want it to be an external load balancer or an internal load balancer. So the way the flows would work is inbound, pretty straightforward, similar to the Kubnet design that we saw. It will hit the load balancer and then it will go to the pod, and outbound it will egress the orange flow, egress using the IP, outbound IP of the load balancer. Now, there is a lot of magic, like I said, happens between from how it hits the load balancer to all the way to the pod. And that's where we introduced the concept of node port in the previous video as well. Basically, the node port, in this case, a 3984 TCP port 3984, each of the nodes are listening on that um, port, and the load balancer will have a backend of the node port, and from node port the traffic will go to this cluster IP on port 8080, and then it would get distributed to these pods on port 80. Okay, so that's how, that's the deep dive of the entire communication, and we will look at it from the command line as well. So let's take a quick look. Our portal is, our cluster is still coming up. So we could look at the YAML files that we will use to deploy this pods, and also these service of the type load balancer. Okay, so that's the north-south flow. And if we were to look at the east-west flow, so for example, the flows coming from on-prem over this site-to-site tunnel, they'll hit the internal load balancer IP on port 8080. And if the flows are initiated from the pod, because the pods have the same IP from the same network as the node, the on-prem would see this pod as coming from the 240.31 IP. Now this is where it is different from the Azure Kubnet. Kubnet, it gets netted to the node's IP address. All right, and in this case, on-prem would see the actual IP of the pod. So when you're defining the networks, the encryption domain of this the site-to-site tunnel, you would use the 172.16.240 space. So let's take a quick look at our cluster. Looks like it did finish. So let's connect to the cluster. And so we'll get the AKS credentials. And now if we run the kget nodes-o wide command, it gives us the 3 nodes that we deployed and their corresponding IP address 1065 and 39. And let's run this get context command again. As you know, as you saw, I had deleted this earlier. Now it's back up here with an asterisk. That means this is the cluster we are going to be running the command against. And let's grab the FQDN. Let's see what FQDN we got. We got this as the full FQDN for the cluster. And now we are ready to deploy our pods. So let's take a look at the deployment.yaml file. It's going to deploy 3 replicas of using this image nginx.demos, and it's going to expose the container on port 80. And as you can see, this is of the kind deployment. So first we'll do the deployment, and then we will expose the service using the type load balancer. As you can see, this is of the types kind service and of the type load balancer. The load balancer would be listening on port 8080, and it would hit the downstream containers on port 80, which is the target port. Similarly, for internal service, we would use this annotation, which shows that an internal load balancer gets deployed in Azure, and it gets, again, it's using the type load balancer. Front-end IP would be that the load balancer would be listening is port 8080, and the target port is 80. All right, so let's go ahead and kick off the deployment. First, we'll create the namespace. Then we'll run the deployment.yaml file, and then let's see what it did. As you can see, that it's creating these containers. So let's hit enter one more time, and all of these pods. So you can see in this output that the node are on the 172.16.240, and the pods are also on the 172.16.240 network. Now let's go ahead and deploy the external service, and then we can run this command with the dash dash watch to see what it's doing. And you can see that it's deploying the external IP, and then you can see that it deployed the load balancer with a public IP, and it would be listening on. We should be able to hit it on port 8080 now from outside. And then let's also deploy the internal service. So I'm going to go ahead and do a watch here, and it's pending on the internal load balancer IP. So behind the scene, it is spinning up an internal load balancer, creating the rules, backend pools, and everything. And we'll look at it in the portal as well. So while this is bringing up the IP. Let's hold off for a few minutes here while this is deploying it. Let's take a closer look at this external service. This describe command is very useful for any type of troubleshooting as well. So what this describe command is telling us is that we have an external service on it's of the type load balancer ingress. This is the IP on the load balancer, front end port, back end, and then these are the endpoints. Sometimes when you are troubleshooting, be sure to check that the endpoints are live and connecting. In this case, this looks healthy, so we should be able to connect to it. And let's run this command one more time to see if we got the IP for the internal load balancer. It's still waiting. So we'll revisit this in a few minutes, but let me show you what it looks like in the portal. So in the portal, if we refresh this, we can see that AKS cluster is deployed. And if you go into this resource group, you'll notice that we have the container registry, the cluster, and a lot of other resources, but we don't see um, the two load balancers. So there is a special group that gets deployed with an MC underscore, and if you resource group that is, and if you look at that resource group, you'll see the two load balancers. The one that says Kubernetes is the external one, and the one that says internal is the internal one. Let's take a quick look at this one, and then we'll look at the internal one. So you could see the front end IP, back end pools, and these are again the node IPs. Okay, and then load balancing rule. If you look at the load balancing rule, you can see this is the node port. So the load balancer talks to the nodes, not the pods. And then outbound, and this is the outbound rule. So when the pods egress, they will use this IP 25.249. Okay, and we'll run those validations as well. So let's see if the load balancer is completed. There we have a front end IP for the internal load balancer. It was pending before, but now it's showing 240.91. So let's go in the portal and validate that. So in the portal, let's go see the other load balancer, the internal load balancer. It should have that IP, the 240.91. And then the backend pools, these are again the node IPs, the load balancing rules, and you can see this is the node port in question. And of course, the internal load balancer will not have the outbound rules. Outbound rules are only applicable to the external load balancers. Okay, so that's those are a couple of validations from the portal. Let's come back here. We'll do the same describe command against the internal service, and you can see that this is the IP on the load balancer. 8080 on the load balancer is mapped to the target port of 80. Okay, and then the service itself, you could see the endpoint itself listen on port 80 over here. So let's take a quick look at, and then just to call out that this port here corresponds to the cluster IP, which is this IP right here. So these are the cluster IP. So if we go back to the drawing board, this is what this cluster IP means. So from the load balancer to the node IP and node port to the cluster IP to the pod. That's how the communication goes. So now let's do a few other validations over here. So we will verify inbound and outbound. So the easiest way to do this is let's clear this out. We'll get the nodes and pod IPs, and we will exec into the pod. So k exec -it, and we'll pick this pod. We can pick any pod. And then important to say that put the namespace, and then we will just do dash dash and sh. So now we are exec into the pod. If I do IP adder, I can see that I have the pod IP. And if I do curl ifconfig.me, this 249, I'm egressing as the IP of the load balancer. So coming back here, this is the outbound IP of the load balancer. So there are two IPs on the load balancer, 25.249, and that was, that was the IP that we saw, 25.249. Okay, so that's the outbound traffic from the pod goes through the load balancer, and let's validate inbound to the cluster. So let's get the service IP again, the public IP. So we can run a curl command against that. Oops, let's run a curl command against and colon 80. I do have a text for address that shows the actual address of the pod, and you can see that we can hit it from outside on port 8080. And if you want to do it in the browser, we can do that as well, just so you see what it's doing. But basically, it's just showing the IP of the pod that we hit, the downstream pod that we hit. So if we go here and paste this, you can see the pod that we hit this time it's just a simple Nginx demo, and it's connecting to that pod. Okay, so with that, let's go back and look at a couple things for troubleshooting in here. And you could for troubleshooting, there are some commands you can look at the full FQDN using this command. You can do kget events. This is very useful. And if there is any issue, you'll see an error like this. If you forgot to assign or apply that contributor role. And there are other queries that you can verify DNS using. You can do a kget service for DNS, and you can see that this is the DNS cluster IP for the DNS service. And finally, to clean it all up, you can do the delete command. Delete. Oops, this is the wrong one. You want to delete the full resource group. So let me fix that. So I should probably grab that from my other. So let's fix this while we are here. And we can clean up and delete the resource group to delete to clean up everything. And so a few closing thoughts on the portal. You can see that um, in this portal, I have documented all of the outputs so that you have it in front of you without having to create the cluster. So all of the YAMLs and the outputs are over here, and the screen captures of the public and the private load balancers are also here. Oh, and that reminds me, there's one other important thing I want to show you in the portal, how in case of CNI, the pod IPs get assigned ahead of times. So let me show you that in the portal real quick. So if we go back here and if I'm in my subnet and if I look at my connected devices and if I search for CNI, you'll see that all of these IPs in the 240 network got assigned ahead of time. And the reason this happens is because I define my max pods to be, if you remember, I defined my max pods to be 30 in here. So it goes ahead and assigns those IPs ahead of time for the pods. And if you remember back to the drawing board here, those IPs are carved up from the same subnet as the node network or the AKS subnet. So that's what the screen capture is showing. So I have all of the screen captures here, so you don't need to spin up the network. The IPs and ports match what's shown in the diagram. And last but not the least, there is the key design points and use cases are defined all over here. Okay, so that completes this session on the Azure CNI. Be sure to join me on the next one where we will cover the Azure CNI overlay. And thank you again for watching. Hope you enjoyed this recording.